The Mediterranean island of Malta operates as a localized laboratory for extreme climate architecture. Buildings here face a constant load of intense insolation, high heat, and persistent humidity. This environmental baseline is severe. The island sustains 3,000 hours of sunshine annually, peak daytime temperatures that often exceed 35 degrees Celsius, and an average relative humidity of 76%. Historically, the local response to these conditions has been a reliance on monolithic limestone and concrete. These streetscapes consist of massive volumes of heavy, solid stone fully exposed to the sun. The core flaw in this construction is high thermal conductivity, the measure of a material's capacity to transfer heat energy from one side to the other. Concrete and limestone are efficient conductors. A bare concrete roof acts as a thermal battery. It absorbs solar radiation throughout the day, and then slowly radiates that stored energy into the interior living space long after the sun sets. This continuous release of stored heat prevents the structure from achieving a natural cooling cycle. Traditional monolithic construction effectively creates a heat sponge. Without interrupting energy transfer through the building mass, achieving passive comfort is impossible. By the mid-20th century, the reflexive response to this heat retention was mechanical. Builders began to rely on air conditioning to forcefully regulate interior temperatures. Cooling a heat-soaked structure with HVAC systems creates diminishing returns. The machinery must work against the radiating energy of the building mass, resulting in extreme energy consumption. The thermal load is only half the issue. Builders must also account for the island's 76% relative humidity. High ambient moisture levels amplify human discomfort by limiting the effectiveness of sweat evaporation. Standard air conditioners struggle to manage this persistent dehumidification load. Replacing these mechanical responses with structural material science addresses the root of the problem. In Malta, this involves a specialized foundational screed layer known locally as contrabate. Re-engineering the physics of this single foundational layer lets a building defeat extreme thermal loads passively. This 3D cross-section represents a standard concrete roof slab. Heat energy moves freely through the solid material. This bare slab registers a critically high thermal conductivity rating, offering no resistance to exterior heat. The first corrective measure is a foam insulation layer placed directly over the concrete. This foam acts as a thermal barrier, preventing surface heat from bridging into the structural slab. However, the foam is structurally weak. It cannot support foot traffic or serve as a final protective roof surface on its own. While the insulation slows heat transfer, it must be capped with a robust, load-bearing material sharing these properties. This is where contrabate is applied. Modern contrabate is applied 30 to 70 millimeters thick over the thermal barrier. Unlike heavy cement, this mixture incorporates lightweight aggregates like perlite or polystyrene beads. Microscopically, these create thousands of trapped air pockets within the solid material. Static air is a poor conductor of heat. By interrupting the conductive path with air pockets, the overall thermal conductivity of the roof or floor is significantly reduced. Fiber reinforcement is often added to the mixture to provide structural stability, ensuring the material does not crack under the expansion of the summer sun. Engineering millions of microscopic air pockets into the mix makes the structural foundation a highly efficient thermal resistor. Heat transfer is only part of the problem. We must also address the 76% relative humidity and the risks associated with trapped internal moisture. When moisture condenses and is trapped inside traditional dense concrete, it creates an ideal humid breeding ground for dark, structural mold to rapidly spread. Typical surface treatments like bleach, white distilled vinegar, or hydrogen peroxide offer only a temporary response. These fail against a systemic issue. Chemicals cannot penetrate dense concrete to kill the deep roots. Polymer-modified contrabate provides a systemic solution to this humidity trap. These additives alter the material's interaction with moisture. The polymers create a semi-permeable structure. This breathability allows gaseous vapor to pass through and vent outside, while external liquid water is physically blocked from entry. Maintaining this microclimate breathability keeps the interior dry, which significantly improves the human perception of cooling. The final physical requirement for this cooling envelope is surface albedo. Albedo is the measure of how much solar radiation a surface reflects back into the atmosphere. Dark-colored traditional finishes absorb solar radiation, forcing the underlying insulation to work harder to maintain interior temperatures. Reflective pigments or light-colored coatings are applied directly to the cured surface of the contrabate to maximize this effect. Data shows that these reflective additives can reduce actual surface temperatures by up to 10 degrees Celsius during the peak of summer. Deflecting solar radiation at the boundary layer provides a primary line of defense, preventing the thermal mass from ever loading with heat. This model illustrates the combined effect of the thermal barrier, lightweight aggregates, breathable polymers, and the reflective surface. In operation, this passive system naturally reduces indoor ambient temperatures by an average of 4 to 8 degrees Celsius. This temperature drop translates into a 25 to 30% reduction in mechanical cooling requirements. Based on Maltese case studies, this can save homeowners an estimated 450 to 540 euros in electricity costs every summer. This structural strategy reduces the carbon footprint of the home and eases the strain on localized energy grids. Intelligent thermodynamic engineering of our structural foundations creates a durable climate resilience that machines alone cannot provide.